October 23rd, 2025, a solar storm erupted on the far side of the Sun. Its shockwave travels at nearly 2,500 kilometers per second. At that moment, the interstellar object Tri-Ilas is hidden behind our Sun, positioned between Earth and a cosmic explosion that no telescope can yet observe. The official forecast warns of radiation storms and increasing geomagnetic danger. But when the three ILS approach their closest encounter, no one can explain what will happen when the alien guest receives a charge from our star. Today, we will analyze the facts and show why this event could forever change our understanding of interstellar objects. At 2000 hours UTC on October 21st, the AC spacecraft at Lagrange Point 1 began transmitting data that caught the attention of all space weather monitoring services on the planet. The levels of electronic flow, usually stable, sharply increased more than tenfold in less than 2 hours. The graphs didn't just rise, they soared, increasing from the background to values corresponding to a powerful event of solar energetic particles. It was not a slow buildup. It was a wave of high-energy electrons arriving ahead of the expected proton storm. The sequence, well known to meteorologists as a classic sign of a major solar eruption, the time was indisputable. The electron surge began exactly when the coronal mass ejection shock wave from the far side of the Sun was predicted to cross the interplanetary magnetic lines connecting the Sun to Earth's orbital zone. The criteria for a radiation storm were met almost instantly. By 22 hours UTC, the NOAA Space Weather Prediction Center issued a warning about a solar radiation storm, reporting conditions from S1 to S3, indicating weak to strong radiation levels sufficient to activate alarms for satellite operators and polar flight routes. For reference, level S1 may disrupt minor satellite functions and necessitate additional monitoring, while S3 increases the risk of single failure events, surface charging, and radio interference at high latitudes. The difference in time between electrons and protons is not just a curious fact. Electrons, being lighter, move faster along the magnetic lines of the Sun, arriving several hours earlier than the heavier protons. This early burst of electrons serves as a harbinger, signaling that the main event, rich in protons, will soon follow. Spacecraft teams hurriedly revised protocols, and commercial satellite operators prepared for possible anomalies. At the same time, ground-based cosmic ray detectors were preparing for what could become a classic reduction of background when the incoming shock swept away galactic background particles. The scale of danger was immediate and global. The electronic flow increased more than tenfold, proton levels rose, and the world's attention was fixed on the Sun-Earth line. The question occupying the minds of all experts was, what caused this energy attack? And can one trace her to a cruel erection racing towards Venus and the hidden interstellar visitor behind it? On October 21st, 2025, the geometry of the solar system created a rare blind spot. While the world watched the sharp increase in radiation levels, 3 Atlas-class objects hid behind the Sun from Earth's perspective. This is the moment of superconjunction, a configuration when the Sun is between the Earth and a distant object, blocking all direct observations. At the same time, the Moon reached a new phase, almost perfectly aligning with the Sun and Earth. As a result, an invisible straight line formed, extending from our planet through the Moon to the Sun and further to 3 atlases now hidden on the far side. Such a cosmic alignment is not merely curiosity for orbital diagrams. With the new Moon and 3 atlases in conjunction, ordinary tools, ground telescopes, and even most space observatories lose their direct visibility. No visible light, infrared radiation, or even radars can penetrate the dazzling light and plasma of the solar disk. For a brief moment, the interstellar visitor becomes a ghost, inaccessible to direct observation. His fate depends on solar activity that will erupt on this side of the Sun. This coincidence is not accidental. When a coronal mass ejection, CME, occurs on the far side, its trajectory is directed almost straight towards the invisible atlases. The comet's path, nearly aligned with the ecliptic, brings it to the center of a solar storm, when it is most vulnerable and least observable. For planetary scientists and heliophysicists, this collision is hidden in plain sight. It can only be reconstructed using indirect evidence, modeling, and the delay in the arrival of energetic particles. On Earth, astronomers mark the date, October 21st, a new moon, superconjunction. They know that in the darkness beyond the Sun, an interstellar object is about to collide with the full force of a solar flare, and the only clues will arrive in data after several hours or days. filtered through the relentless light of the sun. On the night of July 1st, 2025, a faint moving point of light triggered an alert in the automated system of the Atlas Surveys Observatory in Chile. The system marked her trajectory as unusual, but it was the junior team member, an amateur astronomer working on the project, who noticed that the numbers did not match any known comet or asteroid. The object's path was steep, cutting through the stream of planets, and the orbital calculations refused to close. For several hours, the team sent their findings to the small planet center, and for several days, observatories around the world hurried to confirm what the data showed. It was not an ordinary visitor. The designation followed quickly. 3 Atlas, the third confirmed interstellar object crossing the solar system after Oumuamua and Borisov. Its orbit was hyperbolic, meaning it was not bound to the sun and would never return. The numbers were impressive, a slope of 175 degrees, gliding across the plane of the planets, but moving in the opposite direction, with a declination of only 5 degrees from the ecliptic. Early forecasts indicated that the comet would pass near Mars in October and then reach its closest point to the sun at a distance of 0.36 astronomical units on October 29th, moving at nearly 68 kilometers per second. The Earth faced no threat. The closest distance to the planet would be 1.8 astronomical units, a safe margin. However, its interstellar origin made the comet a rare find for Atlas researchers. The following weeks became a real whirlwind of interviews, late-night data analysis sessions, and a sharp transition from anonymous observational work to the center of a global scientific event. 3I Atlas is now undergoing a transformation that only a few objects in the solar system have ever experienced. As it approaches the sun, its exposure to sunlight has increased by more than 7 million times since it drifted in interstellar darkness. The figures are impressive. What began as a stream of energy, less than 1/1,000,000th of a watt per square meter, has turned into a flow. The comet is now absorbing about 735 watts per square meter as it approaches perihelion. This jump in brightness is not just statistics. This is a physical shock to the core, causing rapid changes in temperature, chemistry, and surface structure. Observatories monitoring Tri-I Atlas before it disappeared behind the sun recorded a sharp increase in gas emissions. By mid-September, the production of hydrogen cyanide tripled, reaching about 4.5 times 10 to the 25th molecules per second. The comet's coma expanded, and the dust tail became more pronounced, hinting that volatile ices were evaporating as the comet's crust disintegrated. Such activity is typical for comets approaching the sun. But Tri-I Atlas is not a typical comet. Its interstellar origin means it carries exotic ices and a chemical signature unlike anything orbiting our star. The situation is becoming increasingly tense as the coronal mass ejection front approaches her position. 3I Atlas will soon be affected by an environment that puts even the native comets of the solar system on the brink of possibility. The stakes are high. A sudden jolt of energetic particles and magnetic oscillations can cause unpredictable eruptions or even structural changes. Although the Earth remains safely distant, no closer than 1.8 astronomical units in December, the interstellar visitor now stands in an open space, its fate tied to the fickle mood of the sun. Sunspots in regions 424 and 426, both unusually active, dominated the solar disk in the days leading up to October 21st. Their magnetic fields swirled with complex intertwined loops, creating favorable conditions for the instability preceding a major eruption. As these regions rotated over the eastern edge of the sun, observers noted a steady increase in the flow of X-rays. By October 20th, the most active group had just gone out of direct sight from Earth, but its influence continued to be felt. On October 21st at 20 hours and 24 minutes Coordinated Universal Time, the LASCO C2 coronagraph of the Solar and Heliospheric Observatory recorded the first signs of turmoil. A bright, asymmetric aura began to unfold, rapidly spreading across the instrument's field of view. Unlike the classic symmetrical coronal mass, this ejection moved along an asymmetric arc. The main mass of material burst forth from the far eastern edge, clearly indicating that the eruption was powerful and directed away from Earth. Station Stereo A, located far from the Earth-Sun line, provided an important side view. Its HI and QR images tracked the expansion of coronal mass ejections, showing a dense front moving at more than 2,400 kilometers per second. The source of the explosion was detected at the coordinates of the old active region 426, which was now hidden on the far side of the Sun. NASA and ESA analysts studying real-time data confirmed the eruption trajectory that was not directed towards Earth, but headed straight towards Venus and Comet 3I Atlas. The evidence was unequivocal. The choreographers C2 and C3 demonstrated the full force of the explosion, while the perspective of stereo A confirmed both the speed and angle. Analysts constructed a propaganda cone, overlaying it on the ephemeris charts. The coincidence was striking. A shock front of a coronal mass ejection, modeled with high confidence, was set to cross the orbits of Venus and an interstellar comet within a few days. For the first time, the threat could be traced step by step from the tangled magnetic fields of a sunspot through the expanding corona to a precise sector of the inner solar system. This became the basis for every forecast and alert issued in the following hours. Predicting the path of a solar eruption through the solar system is a test of both physics and timing. As soon as the coronal mass ejection left the Sun from the far side on October 21st, propagation models like ENL were employed to predict the shock course and time windows of impact. Analysts entered the measured speed of the coronal mass ejection, nearly 2,500 kilometers per second, and the launch coordinates from stereo A and SOHO, after which they ran numerous scenarios to build its trajectory. The results converged on a clear outcome. Venus and Comet 3I Atlas were right in the impact zone. Models showed that the shock front would reach Venus between 6 and 16 hours UTC on October 23rd, and the position of the comet would be just a few hours behind. The expected arrival is between 8 and 18 hours Coordinated Universal Time on the same day. A shell of compressed plasma and a tangled magnetic field will follow the comet for the next 6 to 12 hours. The core of the coronal mass ejection, likely carrying a strong southern magnetic field, will follow very closely. Each stage, shock, shell, core, brings its own dangers. Sudden increases in particle flow, fluctuations in magnetic orientation, and the possibility of intense, localized turbulence. For Comet 3I Atlas, the encounter will be nearly head-on, with a normal shock aligned closely to the Sun-comet line. The uncertainty in these forecasts is about 8 to 12 hours and is related to the subtle resistance of the solar wind and the angle of expansion of the coronal mass ejection. Nevertheless, confidence was high. The propagation vector, tracked using data from the coronagraph and heliospheric imager, left no doubt about the correctness of the direction. The Earth will avoid a direct hit, only feeling a light impact of energy particles and a classic decrease in the magnetic field as the shock wave passes by. As the moment of impact approaches, attention focuses on a narrow time window. October 23rd became decisive. The fate of the Venusian spacecraft and the interstellar comet depended on the predictions of the model. For scientists, it was a rare opportunity to observe the unfolding of a cosmic chain reaction, strictly time-synchronized and extending millions of kilometers, ready to deliver its verdict based on yet-to-arrive data. Satellite operators around the world spent hours on high alert after a coronal mass ejection signal. When monitoring stations recorded the first spikes in electrical signals, commercial networks began to take precautions. One of the leading scientists in a large European consortium of geostationary satellites recalls the moment. "We did not see the trigger for the automatic switch to safe mode, but the charging speed on the external panels increased by almost 40% from the baseline level. Our team closely monitored the telemetry. A weather satellite in low Earth orbit reported a brief but measurable charge accumulation on the surface, which was enough to halt the scientific data. There were no major failures, but the risk was real." High-frequency radio operators, especially those supporting transpolar flights, recorded several minutes of signal quality degradation. One of the northern flights over the Arctic reported a brief loss of high-frequency signal, which aviation meteorologists attributed to an ongoing event with solar energetic particles. Meanwhile, in orbit around Venus, the solar probes Parker and Bepi-Colombo were transmitting bursts of data about particles to Earth. Both spacecraft registered temporary spikes in the number of protons and heavy ions as the simulated coronal mass ejection wave passed by. The leading researcher of the Parker group noted a sharp hourly spike in radiation levels that almost exactly coincided with the predicted time of the shock wave's arrival. The Bepi-Colombo magnetometer recorded a sudden change in the magnetic field, followed by a surge of plasma wave activity. These signatures confirmed the models. The shock wave and the shell of the coronal mass ejection indeed crossed the equipment, rather than remaining merely theoretical. For the ground teams, the data became a rare, tangible proof that the forecasts were not just academic. They were unfolding in real time with spacecraft and aviation systems on the front lines. Shortly after noon on October 21st, two earthquakes of magnitude 4.5 occurred near Katowa, Poland, 8 minutes apart. That evening, a tremor of magnitude 3.9 shook the northwest coast of Scotland. There were no casualties, no damage either, just a multitude of theories on the internet. The time frame is so close to the explosion of a coronal mass ejection and the passage of the triple object eye on Atlas that it fueled speculation. Could a solar ejection provoke earthquakes on Earth? Posts on social media multiplied, reflecting a question that has remained relevant for decades. Seismologists quickly responded. The U.S. Geological Survey and the British Geological Survey pointed to tectonic stress as the cause of earthquakes, not solar storms. They referred to decades of seismic data showing that although the double earthquakes in Poland were unusual in timing, they fit established regional patterns. Academic studies that have been peer-reviewed and are accessible to the general public have consistently found no mechanism linking coronal mass ejections or solar energetic particles to earthquakes of such magnitude. According to them, the data simply does not support this theory. Nevertheless, the idea continues to exist. Some researchers keep searching for subtle connections, suggesting that rare electromagnetic effects might push fractures that are already on the brink of destruction. Most scientists remain skeptical, explaining any coincidences as mere chance and the high frequency of both solar storms and earthquakes. An earthquake in Mexico with a magnitude of 8.2, which occurred in 2017 after the perihelion of the comet Oumuamua, is often mentioned by enthusiasts, but major geophysicists see it as merely a coincidence. A similar division forms a discussion around Comet 3, Y Atlas. Some suggest that a coronal mass ejection could charge a comet, leading to eruptions or chemical changes. Experienced comet scientists urge caution, noting the vast difference in scale and lack of direct evidence. At this moment, the fate of the comet remains hidden behind the sun. The arguments remain unresolved, the data incomplete. The next observations may clarify the situation or deepen the mystery. On October 21, 2025, at 2 o'clock Coordinated Universal Time, a coronal mass ejection occurred on the far side of the Sun at a shock speed close to 2,474 kilometers per second, confirmed by images from coronagraphs C2 and C3, as well as stereo A observations. This event coincided with the greatest alignment of Comet 3I Atlas, placing the interstellar object directly behind the Sun from Earth's perspective and exposing it to the expected solar radiation, which varied from 10 to the -7th power to about 735 watts per square meter. NASA ENL models predict that a coronal mass ejection will intersect the trajectory of 3.9 to Atlas within 2 days, but specific effects on its chemistry or structure have not yet been observed. Although data from satellites and probes confirm a surge of high-energy particles, and seismic events in Poland and Scotland were recorded during this interval, no direct causal link to solar activity has been established. The closest approach of Comet 3I Atlas to Earth is scheduled for December 19, 2025, as both bodies move in the same direction. As new data arrives, the scientific community continues to monitor measurable changes. However, many questions about how interstellar objects react to extreme solar events remain unanswered.